Hello guys, and welcome back to your midterm 1 numerical systems recap part 2. We're going to pick up where we left off at the previous part, which is converting from hexadecimal to decimal. There's just one point that I want to bring to your attention before I go on, which is if you are confused about any of the stuff that I'm doing here, please go back and watch the specific video that handles the thing that you're confused about. So let's get to work. So we need to convert 6e here from hexadecimal to decimal. So there you go. We need to do 6e. We need to convert this from hexadecimal to decimal. So the values of these places are at powers of 16, right? Because the value of any digit here, v, equals base to the power of n minus 1, where b in the hexadecimal notation, right, is 16. So this is the second place, so the value of this place would be 16 times 2 minus 1, which is 16, raised to the power 1, which is 16. So the way that we do this is that we multiply these numbers here with their place value, and then we add up all the numbers. So doing this would be equivalent to 6 times 16, right, plus e, and e in hexadecimal is 14 in decimal, right? Okay, so using a calculator, let's do 6 times 16, or let's say 6 times 16, that equals 96. So here we have 96 times plus 14, that equals 110. So this number here in hexadecimal equals 110 in decimal. Now, how do we do the opposite? Even though this is not in the sheet, but I want to recap over that very, very quickly. Can we convert 110 back to its hexadecimal notation? Yes, we can. Just like we do in the binary conversion, right? We will have the quotient here and the remainder here. And the way that we do this is we divide this by 16, record the quotient and the remainder, keep passing the quotients till the quotient is less than base or less than 16, then we pass it as the last remainder, and our hexadecimal number will be all the remainders that we have in this column from the bottom up. So let's do that. 110 divided by 16 equals 6, right? Why? Because 6 times 16 equals 95, and we still have 14. So that equals 6, and we're going to write 14 here. But remember, we're going to write it like this, okay? Don't make a mistake in the exam and write it in a decimal notation. And then pass the quotient, as I said, till the quotient is less than the base, which is 16. 6 is less than base, then we pass it as the last remainder. Now the number will be all the remainders from the bottom up, which is 6e. So there you go, we converted this number back to its hexadecimal notation. Okay, let's go to the next question. So hexadecimal to decimal and decimal to hexadecimal. Okay, we need to convert these 2's complement numbers back to its base 10 or to its decimal equivalent or base 10 numbers. So just to remind you very, very quickly, in 2's complement, if you have a number, if you have 1 in the most significant bit like this, that means this is a negative number. If you have 0, that means this is a positive number, right? So this is negative, this is 0, negative, negative, positive, positive. So let's start with this number. So there are 2 ways to do this. This is 1, 10, 10. Let me drag this up a little bit. So we need to convert 1, 10, 10 into its complement to its convert it to its decimal equivalent. So there are two ways to do this actually. 1, 2, 4, 8, and the last one should be negative in to its complement. So we add up just like we do in the unsigned binary notation. We add up all the numbers except for the last one. It has a negative weight. If you want to know why this is the case, please go watch my video on 2's complement. So this is the first way. So let's do minus 16, right, plus 8, right, plus 2. Sorry, plus 2, and that would be minus 6, right? So you just like the unsigned binary notation, you add up all the ones. The only difference is the one in the last significant bit right here has a negative weight. So this is the first methods. The second method is to copy. So this is here. This is the solution using the first methods, right, of this number. This number here is minus 6. And this is the first method. The second one is copy all the bits from right to left, right, till one is copied, and then reverse the order of the remaining bits. So let's do that, and that would be method 2. So copy all bits from right to left. So copy this till you've found 1, and then reverse the order of the remaining bits. So 0 becomes 1, 1 becomes 0, and then this here would be, using unsigned binary, would be 6, right? And then we add the sign, still minus 6, and that would be method number 2. Okay, so that's how we convert 2's complement to its base 10 or its decimal equivalent. Okay, next. Now we need to convert this base 10 representation to 2's complement using 8 bits pattern. So essentially we are doing the opposite of what we did here. So let's pick a number. What we are doing, we need to convert this decimal number to its 2's complement equivalent using 8 bits. So the way to do this, we're going to do minus 17. Why? Because it looks a little bit hard. So the way to do this, minus 17 to its 2's complement equivalent, is first we need to convert this to 17 using unsigned binary, and then we convert it from 17 from unsigned. We convert it from unsigned binary to 2's complement. So let's do that. So with the algorithm that we have used before, right? I explained this in the first part, so I'm going to go quickly. 17 over 2, that would be 8, remainder 1. 8 over 2, that would be 4, remainder 0. 4 over 2, that would be 2, remainder 0. 2 over 2, that would be 1, remainder 0. 1 comes here, and then so this is the number. This is number 17. 1, 2, 4, 8, 16. Just to make sure, 16 and 1, that is 17. So that is the first step, is to get the unsigned binary, right, of number 17. Now the question says convert it to 2's complement using 8 bits. So we need, these are 5. We need to add 3 more. These are 5 bits, so we need to add 3 more. Now this is positive 17 in 2's complement. We need to convert this to minus 17 in 2's complement. The way we do this, just like we did in the previous example, we copy bits from right to left till 1 is copied and reverse the order. So let's do that. Fortunately, 1 is the very first bit, then we reverse the order of the remaining bits. So 0 becomes 1, 0 becomes 1, 0 becomes 1, 1 becomes 0, 1, 1, 1. That's it. So this right here equals minus 17 in 2's complement, 8 bits notation. Okay, next. We're going to do some additions here. So let me print the screen and copy it over here. So let's do this right here. Now be careful here. It says additions in 2's complement, right? I know it's not asking you whether an overflow occurred or not, but we're going to try to determine that. Okay? So we're going to do this example here and this example. 1 plus 1 equals, first of all, if these are zeros, right, that means these are different signs, because we agreed that if you have 1 here, that's negative. If you have 0, that's positive. An overflow, mark my words, never occurs if you're adding numbers with different signs. It only occurs when you're adding numbers with the same sign. So there will be no overflow here. So 1 plus 1 equals 0, carry 1. 1 goes to the next place. So that's 1. 0 plus 1 equals 1. Radix point. 0 plus 1 equals 1. 1 plus 0 equals 1. 0 plus 0 equals 0. 1 plus 0 equals 1. Okay. So this is the correct answer. Let's do this. 1 plus 0 equals 1. Right? And 1 plus 0 equals 1. 0 plus 1 equals 1. Right? 1 plus 1 equals 0. Carry 1. 1 plus 1, which is the carry, equals 0 and carry 1. Right? This is out. Why? Because these are 5 bits. 1, 2, 3, 4, 5. So make sure that when you're doing this, you're only using 5 bits. This doesn't count, right? If you put 1 here, it's going to be a mistake. Okay? Why? Because you're using 5 bits. Now let's make sure. If we say 1, 2, 4, 8, and minus 16, right? Because there is 1 here. So this number here is minus 16 plus 10, right? Sorry, minus 16 plus 11, so this is minus 5. Why minus 5? Because this is minus 16 plus 8 plus 2, that would be 10, plus 1, that would be 11, so this is minus 17. Now if this is, what is this number? This number is 4 plus 8, that would be 12, because this is 0 here, so that's a positive number, right? So that's 12. Now let's make sure that we are correct. 12 plus, or 12 minus 7, that should 12 minus 5, that should equals 7, right? That should equal 7. 12 minus 5. Let's see what this number, what is this number? 1, 2, 4, 8, 16. Again, this is a positive number here. So why? Because the most significant bit is 0. So 1 plus 2 plus 3, 1 plus 2 plus 4 is 7. So just make sure when you're doing addition, you don't need this one here. You don't need it because it's just 5 bits. Okay. Okay. So let's go to the. Let's how you do addition into its complement. Let's go to the following question. Now the following question is about overflow, right? It's asking you to do the addition and say if an error occurred or not. Now as you can see here, the addition, it's adding numbers with the same sign, right? Positive and positive, positive, and here there will never be an overflow. Because why? Because that's positive, and that's negative. Here they might be. Here they might be. Here they might be. Now, let me make this a little bit easy for you. So he's saying, solve each of these 2's complement notation, watch for overflow. There's an easy way to do this, and I'm going to tell you how. Print the screen. Let's go here. Okay. Now, this is a 4 bits, right? Because look, all these are 4 bits, correct? So this is a 4 bits 2's complement binary system, right? And we agreed that in a 2's bit, in an in bits, in an in bits 2's complement binary system, the system is able to represent numbers ranging. The system is able to represent numbers in an in bits 2's complement binary system. The system is able to represent numbers ranging from minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1, right? So if we're talking about 4 bits, that would be minus 2 to the power of 3, which is 8, minus 8, to plus 2 to the power 3, plus 2 to the power n minus 1, which is 8 minus 1, so that would be 7. So a 2's complement 4 bits binary system is able to represent numbers ranging from minus 8 to positive 7, right? Why is this useful? Because I know the range now here is minus 8 to plus 7. So even before doing the addition, right, this 7 here, right, and this is 1. So I know decimally this is going to come up to 8, which is above the limit that this system can represent. But even if we want to do it manually, so this is how we're going to do it. Sorry. So 1 plus 1 equals 1, carry 1. 1 plus 1. Oh, I made a mistake. Made a mistake here. Sorry. Yeah. So again, the mistake is about the addition. So again, we said the range is minus 8 to plus 7. 8 to positive 7. So the mistake was in the addition. 0, 0, 0, right? So again, I know that there will be an overflow here because 7 plus 1 equals 8, and this number, this system can only represent up to 7. But let's do it manually. So 1 plus 1 equals 0, carry 1. 1 plus 1 equals 0, carry 1. 1 plus 1 equals 0, carry 1. So the 1 goes here. There you go. That is an overflow. I'll tell you why. Because you know there's an overflow when you're adding 2 numbers with the same sign, positive 7, positive 1, and the result is a different sign. This in 2's complement, it has 1 in the most significant bit. This equals minus 8. See? That's a mistake here. You want to do another one? Why not? Let's do a negative. So 1, 2, 4, minus 8. So this number here is minus 8 plus 2. That's minus 6, right? Why? Because minus 8 plus 2. So minus 6 is minus 12, right? Again, without even adding them, I know there will be an overflow. Why? Because this system is only able to represent minus 8. But let's do it manually. 10, 10. Okay. 0 plus 0. Now, watching for overflow is this here comes as 0. That means an overflow because negative, negative, and 0 means positive. So 0 plus 0, that is 0. 1 plus 1 equals 0, carry 1. It goes here. And 1 plus 1 equals 0, carry 1. See, this one is out because we're only using 4 digits, right? So this doesn't count here, right? Now again, this number in if this is -6 and this here is -6, right? This number in 4 bits 2's complement is +4. So that's a mistake. Now, if you're a little bit confused about this, I advise you to go back and watch my videos about the 2's complement. Let's go to the following question. Okay, we're done with this here. Now we need to do this. We need to convert the following excess 8 representation to its equivalent base 10. Okay, so how do we convert this to its equivalent base 10? Let's drag this a little bit up. Let's drag this a little bit up. Oh, we are running out of space. Click here. So let's take this one. Let's take this number right here. Sorry. So it says this is 4 bits excess 8. We want to convert it to its base 10. So to convert an excess from excess notation to base 10, what we need to do 2 steps. First, we convert it to its to unsigned binary notation, and then we subtract the excess. So one, convert this to unsigned binary. 2, 4, 8. That would be 9. So first step 9, which is convert to unsigned binary. This is first step. Second step, subtract excess. So 9 minus 8 equals 1. That's it. Subtract excess. Excellent. So this number here in excess 8 notation is +1. Okay. What is this number then? This might be a little bit hard. Okay. So excess 8, right? So we need to do this excess 8. Convert this to unsigned binary, that is 0. Minus excess, -8. So this is -8. This number here, it's -8. You get the idea, right? Okay. Want to do another one? Let's do this very quickly. 1, 2, 4, 8. So converting this to unsigned binary is 8 plus 2, that is 14, minus 8. That would be 6. Okay? So on this number here, because 14 minus 8, yeah, this number here in excess 8, that is 6 in decimal. Let's do the opposite. Oh, I'm sorry. So now we need to, we're here now, we need to convert these decimal numbers to its excess 8 form. Okay, now I know we're just talking about excess 8 here, but here we need first to check how many bits is excess 8, and to determine that, I know that it says excess 8 here 4 bits, but I'm trying to give you a rule or a formula that you can use to figure out whatever the excess that you have, you can figure out the number of digits, right? So let's drag this up a little bit. The number of bits in any excess system, n, equals log base 2 of the excess, right, plus 1. So the number of bits here, since this is excess 8, will be log base 2 8 of 8 plus 1, which equals 3 plus 1, which equals 4 digits. So now we know that here we need 4 digits. Okay, so to convert from decimal to excess, let's start with, let's say, -8. First, you add the excess and then convert to unsigned binary. So 8 plus 8 equals 0. Okay? And then 0 in unsigned binary notation, 4 bits, is like this. Right? So -8, and if you convert -8 to excess 8, it will be like this, right? This is -8 in 4 bits excess 8 notation. Let's take another one. Let's say 3. Again, you add the excess, so that would be 11, and then you convert 11 in 4 bits to unsigned binary. 1, 2, 4, 8. So 11 would be 1 here, 1 here, 1 here. There you go. So this here is 3 in 4 bits excess 8 notation. Okay? Okay. We're almost done. Floating points. So we need to convert these decode these floating point patterns using the floating point format. So let's say we will do this pattern right here, right? You copy this, copy, and I'm going to paste it here. So that would be 11. Trying to write this number. That is 11, 0. Okay, so that's 1, 1, 0, and then 3 ones, right? And then 0, 0. Okay. So we need to convert this to its decimal equivalent. Now, to remind you, in floating point, we have this digit here is the sign, right? Point here. And this these 3 digits, the following 3 digits, is called exponent, right? Exponent. And then this is the mantissa here, right? Mantissa, right? So first of all, if the sign, this is the sign bit, right? And this is the exponent, and this is the mantissa, right? So if the sign bit has 1, that means it's a negative number. Now, this number here is in 3 bits excess 4. So we need to convert it back to its decimal. So that would be the second step. First step, check sign. If 1, that means minus. If 0, that means positive. It's 1, that means minus. Convert this number here in 3 bits excess 4. Convert it to its decimal equivalent. That is 5. And the way we convert this is, that is 5 minus 4, because you subtract the excess, right? So that would be 1. That is step number 2, 1. Now, because this number means 1, that means the mantissa, right, which is here. We said this is the mantissa right here. We are going to move the radix point 1 point to the right. So the number becomes like this, because this is the mantissa, right? And we moved it 1 point. Why 1 point to the right? Because this number in 3 bits excess 4 means 1. So we move it 1 point, right? So to convert this to decimal, this is going to be, this is 1, and this is half, so that's 1.5. I hope you're not confused. If you are a little bit confused, again, you can go watch my video on the floating point. Okay? Maybe you can do another one very quickly. Let's take this number here. Okay, so let's take this number, which is 2 zeros. Okay, so that's 2 zeros, 1 1 1 0, I guess 0 1, right? Okay. Yeah? So again, this here, this is the sign, this is the exponent, and this is the mantissa, right? Sign has 0. That means it's a positive number. We need to turn this number right here, yeah, which is a 3-bit success 4, to its decimal equivalent. That would be 1, 2, that would be 3, right? Minus 4, because that's how we turn from XS4 to decimal. That would equal minus 1. Oh, so what does minus 1 mean? It means this mantissa here. So the mantissa is here. It's the mantissa, right? It means this point will move 1 digit, but in this direction. Why? In the previous example, it moved to this direction. Why is it moving to this direction right now? Because it's a minus. So the number becomes 0 1 0 0 1, because if you move this 1 digit, it means there is a 0 here, right? Okay, so again, how much is this? So radix point 1 0 0 1, that is half, that is 1/4, 1/8, 1 over 16th, 1 over 32. Okay, so that's 1 over 32 plus 1/4. Maybe we use a calculator to do that. 1 over 32 plus 25. Yeah, so it would be this number. Okay, 0.28, 0.2812. Point here, that would equal 0.2812. This is this. Okay, excellent. Okay, so the last thing that we have here, and then this tutorial would be over, is converting these values again back to the floating point format, right? So I'm going to take a negative number, which let's say I'm going to take this minus 3.5. So this is how we do it. Okay, we need a white space right here. Okay. Let's need some white space. Okay, so very quickly I'm going to upload another white sheet. Sorry guys, that would be 2. There you go. Sorry for that. There you go. So again, I'm sorry for that. 3.5 minus 3. So minus 3.5, we want to put this into floating points. So let's convert it to binary first. We now know that 3 in binary is this number, correct? And half is this, right? Because this is half. So first we need to produce the mantissa, right? So if this is going to be the number, so the mantissa will be like this, right? And all we need to do is, because this is the mantissa, right? It's 4 digits. And this number, keep in mind, it has to be 1 all the time. Now, the exponent need to be +2. Why? Because when the exponent is +2, that means the radix point will move 2 points here, and it will give us exactly this number. So to convert +2 to 3 bits excess4, we need to add the excess, so that would be 6, and then add the excess, 2 plus excess4 equals 6, and then convert to unsigned binary. Unsigned binary is 0, 1, 1. So that becomes the exponent. What is the sign over here? The sign is minus. That means in the sign we need to put this. So here's the conversion. 1, 1, 1, 0, 1, 1, 1, 0. So this number here is equals 3.5 if you use floating point notation. Floating point. I'm sorry that this tutorial took a lot of time, guys. Thank you for watching, and I guess I'm going to see you in the circuits tutorial. Thank you.